Hello, welcome to the course on power electronics with wide bandgap devices. Today I am going to discuss about another application of wide bandgap devices, which is in renewable energy source applications. So in the last lecture I have discussed about integrated motor drives, their challenges and how use of wide bandgap devices can be beneficial for that application. Now when we consider renewable energy sources, the first thing comes to our mind is solar PV or the wind, right? Now, when we consider solar PV or wind, obviously, the one of the important thing of this applications are it is expected to have like high power density system, high efficiency, low power loss. These are the properties are kind of needed from the power converter, right? So as you can see, this rapid development of renewable energy systems, especially photovoltaic energy and wind energy, poses increased requirement of high power, low loss and fast switching. Now if we use silicon devices, obviously there are limitations with respect to the wide bandgap devices. This fast switching part obviously will be restricted when it will go for high power level. Now this high power level, so generally what are the power level kind of expected for this wide bandgap devices applications or the renewable energy sources use? So what kind of power level we are focusing on? So if I consider for solar PV, let's say just take an example of solar PV, any solar PV based system. So like there are different power categories, right? So now, so power levels, if I try to classify, if the power, so let's classify the power and the applications where we need this kind of power level. So the minimum power level which can be focused on other than like single solar PV which is connected to light applications and all. So mostly like single like power level we need to consider if it is less than 10 kilowatt, right? It can be anything between 0 to 10 kilowatts, like 500 watts, 1 kilowatt, 1.5, like that. It can be anything. So generally this is in use for like mainly household applications, right? And it can also be used for small commercial application, not large commercial applications, right? Mainly it is focusing on residential kind of applications or small commercial. Now this power level can be more than 10 kilowatts. Now another important thing is that when we are considering 10 kilowatt, then what is happening? It is basically connected to single phase inverter. So single phase inverter kind of application, single phase or the split phase inverter kind of application. So there this kind of solar PV will be connected. Now if the power level is between 10 to 100 kilowatts, power level can be in this particular range, right? So here also, so basically here it is mainly focusing on a small commercial application, not residential, mainly small commercial application. So it is considering three-phase inverter connection which is having 208 volts in that particular level. Right, now the power level can be 100 to 250 kilowatts. So now when it is going to 100 to 250 kilowatts, then also it is connected to three-phase inverter, but the power level is much higher. So the voltage level of this particular inverter will be either 300 VAC or the 600 VAC. So it will be for large commercial applications. Right. Now, again, the power level can be more than that. It can be 250 kilowatts to 1 megawatt. It is connected to same three-phase kind of connection, which is having voltage level of 300 VAC or the 600 VAC. This is basically focusing on the connection with the utility grid, the grid connection. So these are the different power level. As we go for high power level, this fast switching limitation will come using silicon devices, right? And also losses will increase, right, at high power level. So that is why it is important to look for the semiconductor devices which will have properties like wide bandgap devices. So this will help the system to operate at high frequency, right? So this will improve the system power capacity. So basically power density will improve, efficiency will improve, and then reliability also will improve, right? So that is why the wide bandgap devices will be suitable for renewable energy source applications. Now this recent commercialization of the silicon carbide and GaN devices has promising opportunities for meeting all the requirement in renewable energy applications. So the features which wide bandgap devices are having, that high voltage blocking capability of silicon carbide devices, ultra low switching losses. So this is very important to operate any like system at high frequency. Then fast switching speed, high allowable operating temperature. So all this thing enables these devices to use for high power renewable energy source applications. But this is not the only advantages which we are considering renewable energy sources. These are the some advantages. Another thing I'll discuss. So the like there is like also there are also challenges for using wide bandgap devices in renewable energy applications. So what are the challenges? So when we consider this application, the fast switching speed will cause the problem of electromagnetic interference, right? So if these renewable energy sources are not designed properly, anyway, like renewable energy sources, when it is connected to utility grid, so the connection itself can cause the problem of EMI, because you know the renewable energy sources, it will be connected in a place. From there the converter, in order to connect it, there will be some distance which need to be like that distance related problem need to be sought out by using the filter. So like if any noises which arise due to the long wire connection and all these things, again like that is at low frequency operation by when we consider silicon devices. Now if we consider wide bandgap devices, we will be going for higher frequency, then this kind of problem related to electromagnetic interference that will increase. So that is one of the main challenges to use these wide bandgap devices for renewable energy source applications. Now, as you know, like the problem of EMI. So obviously, I mean, this will degrade the performance of the overall system, and also it will be difficult to meet the industrial requirement. Means like whatever specifications is given as per the standard. So maybe after using filter also, it will be difficult to attain that kind of requirement, right? Now, this is one problem. The second is that the high change rate of the converter output voltage, that means dVdt, and current, that is dIdt. So this is dVdt and this is dIdt. So this dVdt dIdt problems associated with over voltage on load terminals will occur if stray capacitance and inductance in the power circuit are not minimized. As I have already discussed in previous lectures, so what are the effect of these parasitic capacitances and inductance, and while designing PCBs, how we can actually minimize them. So those problem need to look after. So if at high power level, so these problems will become quite significant. and then the problem of DVDT and DIDT will come, and then it will be very difficult to use the wide bandgap devices for high frequency renewable energy applications. So this improvement of this performance by extensively use wide bandgap devices is counter to reducing the system cost due to presently high market price of the wide bandgap devices. That already you know that cost of this devices is much higher than that of the silicon device. But like the advantage of these devices with respect to reduction of the passive component cost and the like requirement of heat sink can be minimized, so that overall system cost can be reduced down, right? So this is another disadvantage. So mainly three disadvantage here, not disadvantage, basically challenges you can say. So this we need to solve. These three you can see here. One is EMI, another is DVDT DIDT. Already I have discussed with you how to solve this DVDT DIDT related problem. But that discussion was with respect to device. Now when we go for high power application, high power means around 1 megawatt in that level, right? So then how to solve this DVDT DIDT problem at that power level while the device is operating at high frequency, that we need to explore. And the third thing is the cost part, that we cannot do anything, but yes, we can actually optimize size of the remaining component in the converter other than the device part, so that overall cost can be reduced down, right? So these are the three challenges you can always see in this application. Now application, so system cost, as you know, it will be higher with respect to power converter. Then what can be done? One possibility is that we can actually use hybrid kind of device instead of pure wide bandgap device or pure silicon device. I'll discuss that in details how this hybrid device connection will be. So basically in any like place wherever the device need to be connected in the converter, so there instead of using the pure wide bandgap device, 2 3 devices can be connected in parallel. So out of 2 3 one can be wide bandgap device, so that we can have advantages of wide bandgap device, and then remaining can be silicon devices, so that price will not be high, right? So this can be one of the solutions. The temperature coefficient of the silicon carbide device enable the possibility of paralleling of these devices to configure the high power modules. As you know, like at high power applications, so basically we need to use silicon carbide device instead of silicon device. So the temperature coefficient of this silicon and silicon carbide are quite close, so that it will be possible to connect them in parallel. But if it is GAN, then we have to look like how to connect that in parallel and what kind of challenges we will face, right? This hybrid power module can achieve quasi soft switching and therefore be able to significantly improve the converter efficiency at light load and medium load conditions. The efficiency advantage of the proposed hybrid power module for RES power converters can be useful for like applications related to this solar PV and wind. Okay. So this is this is proposed in one paper, so which I am actually taking here as the reference. So this paper I have listed in the reference list. So there they have shown that this hybridizing of this device, benefit how much benefit we can get and what kind of challenges we will face. Okay, so now as I told you, like hybridizing means what? So basically when we say hybrid device, right? So basically what we mean, so since like we are considering high power, considering only silicon carbide type of wide bandgap device in parallel connection with the silicon, so that is what I am drawing here. So it will be connected in silicon and this part can be connected like wherever it is needed to connect. So basically this entire part will work as single device. So this is like what we consider as the hybrid kind of device. Now let's say one application of solar PV. So let's consider solar PV application. For 250 kilowatt power applications, right? 250 means it can be anything like large commercial or maybe utility grid connects, any like whatever you want it to be, so there you can use it. So now here one NPC converter is used. So what is the configuration of NPC converter? So NPC converter generally, so like it is used for like high power applications. So where, so this is the solar PV. It is connected to the filter part here. Now here there are like different modules connected. So I am writing here H1, H2, H3 and H4. Okay, now like this three legs will be there similar to that. So let me just draw this H5, H6, H7, H8, then H9, H10, H11, 12. Okay, so this is how it is connected, and then there will be obviously there will be diodes. So these diodes will be connected this way. So now from the midpoint of this capacitor it will be connected to all the diodes. Right. Now different phases can be taken out. So let me take different color. So this is one phase, this is another phase, and this is another phase. Okay, let's say this is A, B, C. So now here you can see there are different modules which I have drawn here, H1 to H12. So you can see this is H1, this is H12. So out of like this 12 modules are there. Now these 12 modules we can actually consider either single switch or hybrid switch. Single switch means like it can be either silicon switch or silicon carbide switch, or maybe hybridizing as I have shown here in the single device. So in this, so what authors have done, so they have actually considered this hybridizing of the device. So how they have considered this hybridizing? So let me just use this H1 to H12. So they have used the hybridizing device. So there are actually 4 devices which are connected in parallel. So one is here, this one is silicon carbide MOSFET. So this is connected in parallel with silicon devices. So this is 3 silicon devices are connected in parallel. Okay, so these 3 are silicon IGBTs. Right. Now this is not the only thing. Means we can definitely connect in parallel, it will operate fine, that is not a problem. Here something has to do with the gate switching signal. So how this gate switching signal is connected here? So basically, so you can see here, so this is like, let's say this is silicon carbide S1, and then silicon IGBTs, they are S2, S3 and S4. So the gate signal which is provided here to the gate of this devices, right? So then it is provided such that there will be some turn on delay provided to the silicon devices. So basically it will go to all the silicon devices, S1, S2, S3, S4, these 3 devices. Now the gate signal of this silicon carbide MOSFET, there will be providing some turn off delay, right? So it is provided to the silicon carbide MOSFET. So turn on delay means like silicon carbide MOSFET will turn on first in order to achieve the benefit of soft switching, that is already mentioned here. You can see here quasi soft switching in order to achieve this. Now this turn off delay it is provided means like silicon IGBT will turn off first and then silicon carbide MOSFET will turn off. This is again to achieve the benefit of quasi soft switching, right? So this is how these devices are connected. Let me just show you the switching cycle, how it is going to be when I mean that like turn on delay or turn off delay. So whenever the gate signal is provided for silicon carbide MOSFET, let me just write this in this way, gate of silicon carbide, right? So let's say this is on for this much time. Then the gate of silicon IGBT, then there will be some turn on and turn off delay. So let me just give this as turn on and turn off delay. I hope this color is visible to you. So here I'm going to use different color so that it will be clear for you. So this is gate of the silicon, and this part like part which is close to turn off, this is turn off delay, right? As I told you in the previous slide, turn on delay, right? So this is how the devices are operating in order to achieve the benefit of this quasi soft switching, right? Now if we provide the gate signal like this, then what will happen to the current? Just a minute. So current for this silicon carbide MOSFET, so basically current, just a minute, of silicon carbide, so this will look like, so initially there will be some peak current, during that, because not basically it will take some time to reach that peak current. I'm not drawing here, so it will go to the maximum point when there will be turn on delay and turn off delay. So the entire current will flow through only the silicon carbide switch, because silicon devices are not on in that time. So this is the entire current which is flowing through the silicon carbide switch. And now current through this silicon IGBT, so this will be this will be this. So here, so the current difference which you can see here, so like in this particular point during the turn on delay, so the additional current will flow through this silicon device. Now this, I hope this is clear to you, like how this is working. This is due to the turn on and turn off delay, and that we are providing in order to get the advantage of this hybrid switching. Right. Now how this voltage of these devices will look like. So this voltage you have to think about. Now you will think probably, the current of the silicon IGBT, it is actually starting late. So that means this voltage, let me just write down first, this voltage of IGBT or MOSFET, or maybe I can just write silicon carbide or silicon. So it will be same, like, because we are actually considering the devices which are connected in parallel, right? So this will remain like this until it will, like, again all the switches are on. So since it is connected in parallel, once one of the devices is conducting, so it is kind of like behaving like short circuit. So the voltage across this device will be 0. Since all the other devices are connected in parallel, so voltage across those devices will also be 0. As you can see from here, if this S1 voltage is 0, so that remaining like switches, even though it is not conducting in that particular time, turn on and turn off delay, so that time also it will be 0. Right. So this is how we are actually achieving this quasi soft switching part. Okay. So yeah, so this is the benefit of this. So this can be used. Now by using this gate switching signal, like in order to have the advantages, so we can see anyway, like the switching losses are reducing and efficiency is increasing. How the efficiency is increasing? So now if we have to comment on the efficiency part, so efficiency part, it is increasing 2% in light load. Light load means it is around 25% of the 5% of the 250 kilowatts. And now in full load, so basically in rated condition, it is achieving 1.2% efficiency improvement. So these are the improvement we are getting because of this hybridization. So this, obviously it is beneficial, like 2% of 250 kilowatt, it's a lot, right? So you can see this is 250, so you can just 2.5 multiply 2. So you can see that 5 kilowatt of power you can actually save, or maybe output will be 5 kilowatts more just by using this hybrid kind of switches. So it is like nothing else we are considering. The same converter prototype, only the switches are changing, and also the like gate signals, like we need to give some delay time. So for that is actually changing. Other than that, everything remains same. If we now in this hybrid condition also we are achieving some efficiency improvement. So if we can go for like complete wide bandgap devices, obviously by solving this EMI, DVDT, DIDT problem, so then the efficiency improvement will be much higher. Obviously this is much more beneficial to use this kind of switches for renewable energy applications, right? Now this was with respect to solar PV. Now if we consider wind applications, so I'm just considering two applications of renewable energy sources, because like these two are the common applications for renewable energy sources. So other applications you can go through, like if it is available, to see the benefit. Here also in wind applications also, it is by using the hybrid kind of switches. So how this wind application looks like, so you can see here, so there are actually, this will be connected to DFIG. So this is not the part we are interested in, but the part which will be coming after the DFIG, that is the filter part, input filter, and then it will have the converter part. Rotor side converter. Grid side converter. So this configuration also I have taken from literature, and I have listed it in the reference, so you can go through in details if you are like interested in this kind of application. Okay, filter part will also come. Right. This rotor side converter, it is basically rectifier, and grid side converter, it is inverter. So like three legs rectifier and the inverter are in use. So full control rectifier is in use. So here the configuration, it is having three different legs, right? Like this. So basically 6 switches. Now out of the 6 switches, for rotor side converters, let's say this is S1, S2, S3, S4, S5, S6. How this S1, S2 look like? So it is actually combination of silicon carbide with silicon. Again the MOSFET and IGBT combination. This is silicon carbide and this is silicon. And the grid side converter, the similar kind of configuration, but it is inverter kind of 3 legs inverter. Now here the configuration is such that, so here one silicon carbide device is connected in parallel with the 5 silicons. This is silicon carbide and remaining 5 are silicon. Okay, sorry, this is silicon. Only one silicon carbide, 5 silicon. So here the rating of these devices are also very different. So you can see this is the case 300 ampere 1.2 kilovolts. Here it is 1.2 kilovolts and it is having 150 amperes. You can see here one of the important things is that silicon carbide rating is much higher than that of the silicon in terms of current. Voltage ratings remain same. So the reason is that silicon carbide initially, when there will be on, like after turn on delay, the silicon will be on, so the entire current should pass through the silicon carbide device. That's why rating of this device, current rating, is much higher, as you have seen in the previous slide. So here in this case also it is the similar kind of concept. So basically silicon carbide is 300 amperes 1.2 kilovolts, and here like much lower voltage like 150 amperes silicon devices are connected in parallel. So this kind of hybridization again will give efficiency improvement, right? So these are the applications of renewable energy sources. You can actually go through the references. These are the references for the this slide. So obviously there is like clear benefits of using these devices as like at this moment as hybrid kind of switches, as part of the hybrid switches. Later on, like if the all the challenges can be like whenever it will be addressed, so that time only wide bandgap devices can be used in order to get complete benefit of the wide bandgap devices in renewable energy source applications. Okay, thank you. That's all for today.